Okay, and let's share my screen. Hmm. Okay, so you guys can see my screen now?
Yes.
Okay, very good. So, yeah, so today's topic is coloring and weights. Um, by the way, if my audio is ever bad, please let me know. I'm trying a new setup, so okay. Oh, okay, Kareem, you've joined, thanks. Okay. Yeah, so today's topic is coloring and weights, but before we do that, I want to review this problem from last week's homework. Okay. So this is a problem that I put in the double counting section, right? So let's see, what does the problem say? It says that we have a tournament, which is a complete directed graph, and there's a condition on this tournament, right? So the condition is here. So we can see it here. Um, that there is no bad company. So what is a bad company? A bad company is um, so four players where one player was defeated by the other three, and the other th those three players form basically they form a cycle. So yeah, let's just draw what that means. A bad company means you have something like this, where there was one player that was defeated by the others. So I will direct the arrow so that it's pointing towards the loser. Okay. So a bad company is something like this, where you have a player that was defeated by the others, and then among the other three, you have a cycle. Okay. So that's a bad company. And we are told that there are no bad companies. And assuming that, you want to prove this, it's very interesting inequality, that the sum of wins minus losses cubed is greater than or equal to 0. So, okay, this problem is hard because you need to figure out what this expression is counting. You know, on other problems, you're trying to count something or bound something, and then you just do it. Here, you are given the expression first, and you need to figure out what does it count. That's the game here. So let's look at this expression. The first thing I'll do is I'll write W minus L cubed, and I'll break it like this, as W cubed minus L cubed plus 3 times WL squared minus W squared L. Is that right? Um, yes. And I'll think of each of these parts as counting something different. Okay. Um, So let's think about the first part. Okay, this W minus W cubed minus L cubed. So what am I doing? I'm saying, what is the meaning of the expression I equals 1 to n, WI cubed minus LI cubed?
It's just zero.
Uh,
No,
this one is not
no.
0, right? But you're right, you're right, something related is 0. So what is the thing that is 0? Abdullah, you claim that this is 0, and I'm claiming the thing
Oh,
is 0, but
yeah.
Yeah,
something.
because the number of losses is equal to the number of wins every time
No.
a person. Yeah.
But we're cubing. So the thing
Yeah,
that is
cube.
0, so this I will claim is not true. But
Oh,
the
that sounds good.
but the thing that is 0 is if I do wins minus losses.
Yeah, that is true. That is
This one is true. But if I cube it, it's not true. Okay. And you're right. So this is because total wins equals total losses. But there's something related which is true, which is okay, what is it? Where is my which is it's true that if I do WI squared minus LI squared, this one is 0.
Yeah.
Okay. And this was an exercise from that we discussed last time, but let's sort of review why it's true. The idea is what? Um, Yeah, so what's the idea? You know, I always run out of space. I don't know how to create more space, but let's see. Let's duplicate this page. Okay, now I can create more space. Okay. Okay, so why is this true? Well, the idea is it's easier to prove. Okay, well, there are many proofs, but I want to give a combinatorial proof, one that involves counting. There's an algebraic proof, but I want to give a counting proof of this. And the counting proof is basically you understand that this is equivalent to the following identity. It's equivalent to Wi choose 2 minus Li choose 2 equals 0. Does it make sense? I'm using the first expression. So given the first expression, the second two are equivalent. Okay, because okay, what is W choose 2? It's like W squared minus W over 2. Okay, so the linear parts will cancel and you're just left with the quadratic part. Does it make sense?
Yeah.
Okay. So now why is the second expression true? Okay, I want to give a combinatorial proof. So I want to say that sum I equals 1 to n, Wi choose 2, this counts something, okay? And sum I equals 1 to n, Li choose 2, these count the same thing. That's what I want to say. They count the same thing. So what do they count? Look, what's the idea? When I'm counting wins choose 2, what I'm doing is I'm saying, okay, I look at a player and I look at the 2 wins they have. So they have many wins, but I pick 2 of them and I'll get a triangle. Okay. And the point is, okay, it doesn't matter. Okay, you have to be a little bit slower. So it doesn't matter how this last edge is directed, right? So my player is here. This is I, and it has 2 wins. No matter how that last edge is directed, it's an acyclic triangle. So like this versus this. These are both acyclic triangles. So my point is both sides count acyclic triangles. Okay. So this argument we went over last time, so I didn't go into too much detail, but hopefully we recall what it is, right? So
Yeah.
yeah. Okay, so that's the idea. That's the idea for proving this one, right? So now what? Now I want to talk about, well, we want to talk about the cubic version. This guy, what is this? So what's the idea? We want to count something, right? So it's better to, instead of having this W cubed minus L cubed, it's better to have the following. It's better to have Wi choose 3 minus Li choose 3. This thing. This is closer to counting something, okay? And okay, the point is, what is the relation between these two expressions? I mean, I'll leave it as an exercise, but so yeah, this will be homework, I guess, or we can talk about it now if you want. But my claim is this is just 1/6 of the sum from I equals 1 to n of Wi cubed minus Li cubed. Okay, and it's the same idea as before. Like when you take the binomial and you expand it, you'll have a cubic term with 1/6, and then the quadratic and lower terms, they'll cancel because of these identities. Right? Does it make sense? Maybe should I say more or
Yeah.
okay, so I don't want to go into too much detail because it's a lot of algebra, but the idea should be there. Okay, so now the left-hand side, okay, this expression here, this is I claim it's something combinatorial. So what is it? Let's so for this I need a new page. I need to give a new page. Okay. No, I mean I want a blank page actually. Yeah, so let's see what so let's what are we counting here? We're counting, or we're interpreting combinatorially the expression I equals 1 to n, wi choose 3 minus li choose 3. Okay. What does it mean? So what is sum I equals 1 to n, wi choose 3? What does it count? So let's see. So if I have a player, I, and I have 3 wins. Okay, so I'm counting triples of wins like this. But I need to think, if I want to compare this to losses, I have to sort of complete this. Like I have to consider the entire set of 4, right? Okay, and let's see. So what are the possibilities for this entire set of 4? Well, here's my claim. If I have a triangle in a directed graph, 3 vertices, there's really only 2 ways. I mean, okay, there's 8 ways to direct edges, 2 for each, but up to like symmetry, there's only 2 ways to direct them, either cyclically or acyclically. Do you guys understand what I'm saying?
Yeah.
So what I'm saying is either it looks like this. So this is the what am I saying? I'm saying the remaining 3 form a cycle, or it's like this. The remaining 3 don't form a cycle. So I can draw it many ways, but that's one way to draw it. Okay, so acyclic, I guess you can call it. So does it make sense? There's sort of 2 ways to complete it based off of the 3 neighbors of that player I. Are they a cycle or not a cycle?
Yeah, and by the condition of the problem, we can't have the first case.
Okay, great. So let's look at right. So now we want to talk about the condition of the problem. So what does the condition of the problem say? It says a company of players is bad if, no, actually I think the first one is okay because in the first one, there's no player that was defeated by, you see, there's an asymmetry in the condition. It's not, it's not saying you can have like this is only applies to where you have a player that's defeated by all 3.
Oh, yes, yes. I was okay, yeah.
Yeah, but you're right. You're right to think the condition applies because when I do the same sort of thing, so you're right. When I do the same thing for losses, okay, maybe we're getting ahead of ourselves. But you're right. So when I do the same thing for losses, one of the cases won't work. But before we go to losses, I want to sort of like I didn't write an equation here, right? Like I said, okay, this sum W choose 3, it counts something, but I didn't tell you what. Okay, so maybe you guys can help me now. Like what am I counting? So maybe I'll write a claim, and then we can talk about why it's true. I will claim that sum I equals 1 to n, wi choose 3, counts the number of sets of 4 players of the above 2 forms, let's say. Okay, so it counts the total number of like sets of 4 whose win-loss pattern is like this. No, sorry, what did I just do? Okay. Sorry, I just want to make that picture a little bit clearer because I'm having trouble understanding it myself. Okay. Okay, so do you guys understand the claim?
But isn't there a scenario where, like, there isn't a guy who won 3 matches?
Right, so so the point is if I take 4 players there could be many different patterns of what those four players look like. In some of those patterns, there will not be somebody who won against the other three. So for example, you can have I wish I had a bigger canvas, but okay.
Yeah, I know, but like in the two forms, we always have the left end dot is winning 3 matches.
Yes, but I want those sets of four because I'm trying to understand what is counted by this, right? So a set of four will only contribute to this sum if there's a player that won against the other three.
Okay.
Okay.
Oh, and the second drawing is basically the drawing for the losses.
Okay, yeah, so it's
So
a
we will have to prove that the first one can't exist by our conditions.
well, okay, so first it's a good observation that the second one, if I look at the player here, he contributes to the L choose three sum. Now, it doesn't mean that I can't have the first type exist, right? Because remember, I don't actually claim the sum is zero. I'm just trying to understand what the sum is. Okay. And I'll just tell you guys now, it actually does not turn out to be zero, but it does turn out to be positive or non-negative rather. Okay.
Oh, okay.
So it's not going to end up being zero, right? Because it's not like we're trying to prove something is zero, right? So yeah, so you have the right comment, but I don't actually need to prove
I
that.
think
Yes.
isn't the proof just saying that the second drawing represents all the losses?
The second drawing, what?
It represents the losses, not some, but all.
Um, so I don't understand. Can you explain again?
I think the second drawing represents every four pairs that have one who lost against three with the condition of
That's
problem.
right. So are you making a statement about like the bad comp are you using the condition in the problem?
Yeah.
Exactly, yeah. So yeah, you're ahead of me, but you're right. So the condition so when we think about L choose three, we're gonna have two pictures, but one of them won't show up because of the condition. But before I go there, I want to make an important comment, which is we need to sort of okay, maybe it's an obvious thing, but I want to say it anyways, which is in order to prove this claim, I need to say that in each of these sets of four, they only contribute one to the sum of W choose three. And it's because there's only one player in each of these sets that beat the other three. Do you understand the subtlety I'm making? It's kind of maybe obvious, but like we know, when we count W choose three, okay, it's something to do with these sets of four, but to know that each set of four only contributes one to the sum, it's important that there's a unique player in each of these sets that defeated the other three. Should I repeat that statement or is it?
And so the problem is solved by this, right?
Okay, okay. So I think you guys are ahead of me. So yeah, let's just finish it. Okay, the problem is not quite solved. It's just solved that what is solved by this? It's that this is
Yeah,
great.
this is part. Yeah, yes,
Okay,
exactly.
but let's just okay. There's gonna be a recording, so I should give the full steps, right? So okay, so great. So the claim says that the W choose three counts these two types. Great. And then there's an analogous claim for L choose three, which I should write down because okay, so yeah, what is the claim for L choose three? Okay, so then the claim is that sum L choose three counts what? It counts like, okay, this one counts things like this, where you have, okay, there's two cases. Either this is cyclic or this is acyclic. Okay, and what's the point? Okay, so you guys have pointed out to me that, okay, the first case is just not possible because of this is a bad company. Right? This is just not allowed by the condition of the problem. Okay. And the second case, okay, you're right. It's actually the exact same picture, just sort of flipped as this one. Right? These are sort of the same. So what is the conclusion? Conclusion.
The W choose 3 is bigger than L choose 3, thus it's positive.
Exactly right. So the conclusion, so let me write it like this, is that if I take sum I equals 1 to n of Wi choose 3 minus Li choose 3, it actually has a very nice combinatorial meaning. I took this minus this, so all I'm left with is really, this kind of thing. So it counts, okay, let's give this a name. We call it cool companies. Okay, so this is equal to the number of cool companies. Okay, does it make sense? That's the conclusion that we get, that this sort of expression has a meaning. Okay, so it's not zero. It counts something, but the upshot is it's greater than or equal to 0, right? Because if it counts something, it can't be negative. Okay, so that's okay, and so that actually tells us, okay, because of the stuff we did before, it also tells us that sum W cubed minus L cubed is greater than or equal to 0. Okay. Great. So any questions before I continue? So I hope you guys see we did something very nice here, right? We took some kind of expression that's a little mysterious, W cubed minus L cubed, sum of this, and we gave it a combinatorial interpretation, and that helped us. But okay, we're not done. We know that the sum of this guy is greater than or equal to 0, but we still have to deal with this guy. And what I will do is, okay, I think I should leave this as homework because it's very similar. You have to again think about what this means combinatorially. It's going to count some kind of companies again. It's going to count some kind of sets of 4, but you have to think about what. And you have to think about, okay, do I really want to think about L squared or L choose 2 or what? You have to think about that. But it's very similar argument. In spirit, it's very similar. And okay. So yeah, so I'll leave it as homework. So what is the homework? Or I don't know, exercise? What does sum of Wi Li squared minus Wi squared Li count? Okay. And since it counts something, it's non-negative. And that completes the problem. Okay. So any questions about this? Okay, so yeah, so I want to comment, somehow this all started with, this counting acyclic triples, right? It's all, yeah, this identity here is like a surprisingly, but like, it's a nice identity. Okay. Okay, so let's go on to today's lecture topic, right? So let's remind ourselves, what was the lecture topic? So the lecture topic is, right, coloring and weights. Great. So we have some warm-up problems that hopefully you guys got a chance to think about. So coloring and weights. So coloring is a tool that we use to solve combinatorics problems. So the question when you get a tool is how do you know you're supposed to use it? So sometimes it's obvious. So in these problems, it's obvious because the coloring is already there, right? So let's look at problem 1. So problem 1 is let's see. I have a 8x8 board, also known as a chessboard, and I remove 2 opposite corners. Okay, so I'm not going to draw it, you can visualize it. And the question is, can you tile the remainder by dominoes?
We just put that without loss of generality that the opposite corners are the same color And since we have 64 tiles, then we have 32 of one color and 30 of one color. Then since each domino covers one color of like each, for example, black and white, it covers one black and one white, it's not possible because in one case you're gonna have more white tiles covered than black or more black covered than white.
Okay, excellent. Yes, that's exactly the right idea, right? So when I look at what happens in the board, what will happen is, okay, the two opposite corners, I guess you have to check it for yourself. They'll have the same color. Okay, let's say they're both black. I don't know. It could be they're both white. Let's say they're both black. Then there's going to be 30 black and 32 white in the remainder. And of course, then you cannot color by dominoes because every domino color is one black and one white. So this is a very classic problem. I wanted to include it because, like, okay, this is like the reason you can solve the problem is because you knew to color. And you knew to color because it's a chessboard and you always color a chessboard. Okay, so okay. Later we'll see some examples where it's not obvious that you have to color, but it's still useful to color something. Okay, so I want to do another example. So the first one was about tiling. The next one will be about walks. So okay. Generally, if you have problems about walks or about coloring, about walks or tiling, coloring is useful. So let's look at problem 2. So problem 2 is it possible to do let's see. It's called a closed walk because you start and end at this. Oh, no, sorry, no, that's not right. It's not a closed walk. It's a walk that goes from one corner to the other, and it visits everything exactly once. Okay.
It can be solved using contradiction.
Okay.
Yeah.
You end up showing that an even number is equal to an odd number, which cannot be the case.
Okay. Yeah. So
I just looked at the difference, like walked on like X, like the difference is 1 or 0. So 1 if you end up on the same color, and 0 if you end up on a different color.
I don't understand 1 and 0. Are you counting something, or I'm not sure?
Yeah, so we color them 2 colors, like checkboard.
Oh
Same
yes,
idea.
yeah. So it's a black and white coloring, yes.
Yeah.
Okay, so I think there's a lot of solutions. I'd like to hear all of it. Maybe let me just say what I had in. So maybe they're all the same, but what's the point? The walk alternates colors. I go from black to white, white to black, right? Okay, but what's the problem? How many steps do I have to make? I have to make
63.
63 steps, which means I will end on a different color than I started. But I'm starting and ending in black or in white. Okay.
No, such a simpler approach.
Sorry?
That was such a simpler approach the one I did. I did like in total you need to go, for example, 7 right and 7 up. And then each right or each up is only represented by an odd number, TMI plus 1 or TNI plus 1. And you have the 7 for each. And since you have 2 sums with 1 plus on each side, you can just subtract 14. So end up with the sum of an even number plus the sum of another even number is equal to 49.
I see.
Which is a contradiction.
Okay, very good. Yeah, so I think it's good. So that's a very good solution. So it's in spirit, I think it's basically the same solution. The reason I wanted to mention this problem in the context of coloring is because coloring makes it very, I don't know, easy to state, right? Like, what is this? Like, the solution is, okay, 63 steps. They alternate colors. So you must start and end on different colors. Okay, and so that shows you it's not possible, right? Because you start and end on opposite corners, which are the same color. Okay, so Of course, the solution is about parity, and then you can solve it in many ways. But I want to present it in the context of coloring because it's somehow becomes very simple to express when you color the board. Does it make sense? What is the
Yeah.
Okay, so good. So what do I want to talk about now? So good. So these were some examples where you were given a chessboard. So it's like the problem says, look, I'm already colored. But there are some problems where you're not always given a coloring. So let's look at this problem 5. This is one of the warm-up problems, right? So yes, what is the problem? It's about bipartite graphs. So a bipartite graph is a graph whose vertices can be partitioned into 2 sets, such that every edge goes from one set to the other set. Okay, so how do we draw bipartite graphs? Well, okay, we say here's U and here's V. So there's going to be some vertices in U, some vertices in V, and then every edge has to go across, right? That's a bipartite graph. Okay, and there can be however many edges you want. Okay, so that's a bipartite graph. And now you want to prove that a graph is bipartite if and only if it has no even cycles. So this is some kind of classic theorem about bipartite graphs. Okay. So one direction is you can tell from this picture actually. So
Shouldn't it be no odd cycle?
yes,
You
I made a mistake. Yes, so it should say no odd cycles. No odd cycles. Equivalently, if every cycle is even. Okay. So maybe I should clarify what do I mean by cycle, because yeah, there was some confusion about this. So when I say cycle, what I mean is just like a walk that that starts and ends at the same vertex, no repeated edges or vertices. Okay, so like that. Yeah, so like, okay. If I have a graph, like, okay, what am I saying? If I have a complete graph like this, like, okay, this is a cycle of length 3. Okay, this is a cycle of length 4. Okay, to clear what I mean by cycle.
Yes.
Okay, so let's prove that it's bipartite if and only if it has no odd cycles. So one direction is, okay, if G bipartite, then no odd cycles. Okay. So this one, okay, you kind of have to like look at the picture, right? So if G is bipartite, let's say I have a cycle. Let's say it starts here. Okay, it could start on U, but let's say it starts here. Okay, I need to do like it's gonna go back and forth and then come back. It has to have even length. Do you guys see the argument?
Yes.
Like, okay, like there's like okay, it has to go back and forth. So since it goes back and forth, it has to have even length. So every cycle in a bipartite graph has even length. Okay, good. So the hard part is if G has no odd cycles, then G is bipartite. So now, okay, I give you an arbitrary graph. I guarantee you there's no odd cycles. You now have to figure out a way to partition the vertices into 2 sets so that every edge goes between. Okay. Good. Right, so I give you some graph. Let's just, I don't know, I'll give you some graph. And okay, I'll guarantee for you that it has no odd cycles, and now you tell me how to bipartition the vertices. Okay. So any ideas?
We start
We
at
split. Oh,
oh,
go ahead.
okay. We can start at any vertex or node,
Uh-huh.
and then we can go to each edges and color the two colors. So basically, and each edge we reverse the color or it's something simple like change it. So red, blue. So now for each edge going from yes, exactly.
Right, right. So the idea is right. So we just go and we color. We start to coloring, and the only condition is anytime I go to, so like I have to start somewhere. So I started here. And I just go along the graph and I just color. And every time I go along an edge, I switch the color, right? So you can do it. But now there's something interesting, right? Like when I come to this vertex, I could have come at it in two ways, but it's okay. Both will give me red. So when I do this process, the thing I have to make sure is that I never get a contradiction. I will never arrive at a vertex in such a way that I want to color it in two different colors. Does it make sense?
Yeah. This is simple to prove, I think, because for since all the if we have two ways, then since all the cycles are even, uh, both paths will have the same parity of fidgets. The number of fidgets of both paths will have the same parity, and so they will have the same color.
Yeah. So good. So yeah, it should be easy, but let me just sort of make explicit what is the connection to no odd cycles. Like, okay, why is an odd cycle bad? So I'm going to draw a cycle of size 5. 1, 2, 3, 4, 5, right? It's a 5 cycle. So if I start here and I start coloring, if I color blue, and then I color red, and let's say I color this one red as well. Now I come here, I color blue. Now there's a problem here because I want to color it. I don't know what to color it. But why did the problem happen? It happened because I came at it in two ways. And okay, so in the two ways, their lengths have different parity. But another way of saying that is that the total cycle has odd parity. Does it make sense?
Yep, yep.
Okay. So this is something I don't know, it's kind of hard to write into words, but like the problem happened because when you have two paths from the same vertex, from one vertex to another, that have different parity. But that's just the same thing as having an odd cycle. Okay. That's sort of the main idea. So, since I don't have any odd cycles, I will never have a situation where I want to color two vertices. So when I want to color one vertex in two different colors. Okay. So are there any questions? I can maybe, if it's clear, it's okay. If it's not, I can maybe say some more.
Yeah, it's clear.
Okay. Okay, so what was the point of including this example? I wanted to make the point that what is coloring really? It's a way of partitioning, or it's a way of organizing things. So, when we colored red and blue, we created the bipartition. That's it. So at a, high level, coloring is just nothing more than, partitioning something or organizing something into groups. Okay. That's but somehow coloring is something, it's more intuitive to us, but okay. Yeah. Okay. So that was the point of that problem. Yeah, so any questions before I move on? Okay. Great. Let's yeah, so now I want to think about some sort of more fancier coloring. So we'll do a couple problems like this where it's not about chessboard, so we don't really know how to color things, and we have to come up with the coloring that's going to be helpful for the problem. Okay, so yes, here are a pair of problems. So the first one, okay, let's see. The first one says, for which m and n can a m by n board be tiled by 1 by 3 tiles? Okay, and so I allow both horizontal and vertical. Okay, so So that's the question, right? When can I? By the way, does it make sense? I don't know. I didn't define what a tiling is, but do you guys
Yeah,
understand the question?
yeah,
Please,
yeah.
if you
I
don't,
get it.
ask clarifying questions. Okay, so yeah, so how do you? So can you solve problem 3? Which M and N work?
Any M or any M that's divisible by 3.
So do they both have to be divisible by 3, or is only one?
No. Since we have either orientation, it doesn't matter.
Okay, yeah. So first, okay, if M or N divisible by 3, yes. And what if neither is divisible by 3? Can you do it?
No,
The answer is no. And why not? There has to be a reason,
because the M by N is not divisible by 3.
right? So it's a question of area, right? So if 3 does not divide M or N, then 3 does not divide the area, okay? And then you can't do it, okay? Because the area should be divisible by 3. Okay, so no because of area. Okay, so I included that as an example because it doesn't work for the second problem. So for the second problem, I'm now doing 1/4 tiles. So if M is divisible by 4 or N is divisible by 4, then okay, you can do it. But what if neither is divisible by 4? I don't know. What if both are even but not divisible by 4, right? So like M equals 14, N equals 26. Okay, neither is divisible by 4, but the area is divisible by 4. So that's the question here. Can you do it in a case like this? Right, so what if 4 does not divide either M or N, but 4 divides M times N? Can you do it? Probably the label is 3 and 4, right? So any ideas? What about small cases? Whenever someone asks a problem about general M or general N, you should do small cases. So what's the first case?
Two by two.
Okay, so 2 by 2, great.
Yeah, I think it doesn't work because we can count the number of rows have that are that have lengths divisible by 4, and I think it doesn't change module 4.
I see. Okay, so before I get to that, okay, I'll address your. Okay, I'll go the way you suggested, but first let me just point out 2 by 2 doesn't work for like really obvious reasons, right? Like, okay, like you just cannot fit a single tile onto here, okay? And okay, so now your conjecture is that okay, the answer is no, always for such M and N, right? So that's your conjecture. Okay, now let's see. So Kareem, you have some kind of argument for me, right? So can you say it again? I didn't understand.
Yeah, I don't think it's complete, but
Yeah, but what's the idea?
I think it has to do with their length module 4.
The length of
We,
M and N modulo 4, yes. Okay, yes, that's
the length of columns or rows.
I mean, all the columns and rows have the same length. I'm not sure what you mean by length of.
Yeah, but after we color something, it's as if we take it off.
So sorry,
Um,
yeah.
yeah, basically the number of uncolored um, the number of uncolored um, cells in every column module 4.
So are you proposing a particular color? Are you talking about the checkerboard coloring, or are you saying I should have a coloring that has a particular criteria?
Now I'm thinking of counting.
Okay. But you said something about uncolored, so I didn't understand what you meant.
Yeah.
Okay, how about this? Let's give some time to think about it. I think maybe we can take 5 minutes
Okay.
and yeah, let's think for like 5 minutes. It's a good problem, so we should. Okay, should we discuss now? Maybe. Do you guys want more time to think?
Just a minute.
Okay. Okay, would you guys like some more time or shall we discuss? It's okay, we can think for some more time. There's a so shall we discuss now or do you guys want to
We
take
can discuss now. It's fine with me.
Yeah, we can discuss.
Okay. Yeah, so well, okay, does anyone have any ideas they want to, partial thoughts or some kind of like Karim, did you find some way to express this counting idea you had?
Yeah.
So I didn't hear what you said. Okay, maybe the connection is better. You guys can hear me, right? It's okay.
Yeah, I can hear you.
Okay. All right. So what I'll say is, maybe there's some way to do this problem with counting or parity or something, but the point of coloring is sometimes, if you find the right coloring, things become really, really easy. So maybe there's a way to do this problem using some kind of, in-depth counting or something, but there's actually there's a thing you can do which makes it sort of much, much easier to think about. So what I'm going to do is this. So remember, we're trying to color a M by N grid. And so what I'm going to do, so we know, okay, if you have an M by N grid, you can always checkerboard color, but that's not what we're going to do. We're going to do the following. Okay, yeah, so sorry for this drawing. It's really very bad.
Are we gonna do every 2 by 2 has block has a color?
Every 2 by 2 has a, I see.
No.
So Kareem, are you suggesting this coloring where I do A, B, C, D like this?
Uh,
And repeat this pattern?
yeah, like thicker, thicker chessboard.
Sorry? For some reason your audio is not clear
Yeah,
for me.
like a chessboard, but um with four. with four cells, four adjacent cells with each color instead of one.
But if I do it like this, so the problem with this kind of coloring, if I do it like that, the problem is every domino now, or each tile is sort of not, doesn't evenly cover, right?
I think he means each square like A, and then B, like a
Uh,
checkpoint.
Yeah, for each diagonal line you cover.
okay, so, sorry, I don't really, okay, so let me understand. So maybe you mean something like this.
It's just board, but with 2 by 2 cells.
I see. You're saying I do something like this or something?
Yeah,
But then, how do like, when do I stop? Like, how many colors do I use?
or just
We
two.
can do something similar to the dominant problem. We need to find the coloring such that each tile covers all three, for example, all colors at once. We can do this if we color them diagonally.
Okay, great. So, right, so I want to say, so one thing you said is very, very important, which is when we want to color in four colors so that every tile covers one of each color.
Yeah, we can do this. We start the first cell is one, then the diagonal following it is two, then three, then four, then we repeat. Thus, we get it a coloring where each tile covers all four numbers at once.
Right. Great, great. Okay. Yeah. So then, okay, once we get to four, we repeat, right? So very good. So now,
Yeah, but I believe that the 2 colors were enough.
you're saying two
But
colors would be enough. Okay,
Yeah,
so Kareem, you're suggesting maybe we can do it with two colors. We'll
we can.
we'll come back to it. I actually I think I understand now what you were saying. So okay,
Okay,
so Kareem, let's do this one first, and then we'll come back to your solution. Okay, I think now I understand what you were saying because I think we can do it with two colors. But let's do this four color one because I think it sort of illustrates the point very clearly, right? Which is why did we do this with four colors? Because now you look at any tile, 1 by 4 tile, no matter how you place it, it's gonna be one of every single color. Okay. So that's a very important observation because now it means if you can tile the whole m by n grid with these 1 by 4 tiles, there has to be same number of like each color. Does it make sense? Like same number, each of the 4 colors has to appear the same number of times in the board. Okay. And okay, so does it happen? Well, okay, we can go back to like our 2 by 2 example. In our 2 by 2 example, no, it doesn't happen, right? Because like 4 doesn't even appear in the board. Um, we can try like 2 by 6 or something. If we did 2 by 6, what happens? No, it doesn't happen because I think like what? 3 is appearing an extra, like, yeah, like 2 and 4 appear twice and 1 and 3 appear 3 times, right? So, okay, so here's the claim. The claim that, will ultimately solve the problem. So let me state the claim, then we can see why it's true. Um, each color appears equal number of times if and only if 4 divides m or 4 divides n. Okay. So it's not enough that 4 divides the area, it actually has to divide one of the side lengths. Okay. That's a claim. And now we can work on proving it. So this one, okay, this is kind of a little bit of a counting thing. So I'm gonna give you guys a couple of minutes to think it through, but see if you can work it out, right? So yeah. Does it make sense what I want you guys to think about?
yeah.
Okay. So Okay, so yeah, should we discuss now? I think maybe from this picture it should be kind of clear, right?
Yeah.
So I drew m equals n equals 6, which is sort of the first problem case, right? So you want to show that it's not possible to tile this one, and we'll show it by sort of showing the colors don't show up with equal frequency. And okay, so
Yeah.
what do you do? Hello? Yes?
Yeah, we can do 2 or 4.
Yeah, I mean, what do you mean?
Colors 2 or 4.
Oh, you're saying we can do it with 2 colors or something, or?
No, we can do it with color 2 because it appears more than
Ah,
4.
that's what you're saying. Yes, yes. So yeah, you're saying color 2 appears more times than color 4. Um, yeah. But okay, I just want to like sort of draw something here. So I'm gonna look at this block here. I know this block is a 4 by something block. It's gonna be equally colored, so I can kind of throw it out, right? So like this part, you can just say, okay, everything here occurs the same amount of times because it's a 4 by something block. Everything here occurs the same amount of time. It's another 4 by something block. All that's left is this 2 by 2 here. We know 2 by 2 doesn't work. Okay. And this should sort of give you the general argument. If I have m by n, right, any m by any n, okay, so I'm going to be a little bit unrigorous, but hopefully you guys can work this out as an exercise. I can sort of like, okay, I can cut off a part that's like, this is a multiple of 4. And I can also cut off here a part that's a multiple of 4. And what's going to be left is going to be smaller than a 4 by 4. Right? So it'll only work if that's, 0 by 0. Does it make sense? Like I'm saying you can reduce m and n mod 4, both of them.
Yeah, it makes sense.
We can also do that. Like, let's assume that is modular A is a congruence A mod 4. Then the color number A would appear more on like row 1. Then you show that unless n is the multiple of 4, then color number A is gonna always appear more.
So is it in just a row or in the whole thing, right?
And the whole thing, that thing, for row 1, you just show that color number A appears more.
What's
Then you
n?
show that if n, we just put like, m mod 4, and you
Okay.
assume that m mod 4 is equal to A.
Okay.
That A, assign it as the value of the color. Then
So
for
this
that
is
row, it appears more. Like, for example, for this row, we have, whatever it is it 6 by 6?
yeah.
Yeah, see, it's 6 by 6, and 6 mod 4 is 2. That's
Okay.
why color 2 appears more on row 1.
Okay. It appears more in row 1, but the problem is it appears less in row 3.
Yeah, that's why then you show that if n isn't divisible by 4, then that's always the case.
So okay, it's the right direction, but I'm a little okay. I think maybe there's something I'm not understanding, but okay. So I look okay. I have 6 is 2 mod. Okay, so yes, n is 2 mod 4. Now I find 2. It's not true that in each row 2 is appearing more, right? But you're saying that yeah. Maybe can you just say the argument one more time?
I kind of got lost with my own argument. Just give me a second. I'll go back to it once I formalize it a bit better.
Yeah, we can just say that after taking a number of columns that divides 4, we are left with, since we first proved that they both have to divide 2 if neither divides 4, the numbers of, yeah. So we have 2 columns left, and 2 appears on rows with, and from the chunk that's left, 2 appears on rows that are 1 or 2 modulo 4.
Okay.
And we have more of those than 3 and 4, so we have more 2 than 1/4 of the area.
Okay, so yeah, let me just okay. Maybe I want to say the very first thing you said, um, Kareem. I think maybe I should just write that as a claim, um, because I think it'll help clarify our thinking. So we'll say m by n can be tiled. Let's say okay. Suppose um, m is greater than 4, uh, then m by n can be tiled if and only if m minus 4 by n can be tiled. Okay. And sort of by induction, okay, m by n can be tiled. So, okay, and then by induction, m by n can be tiled if and only if I'm going to call it m bar by n can be tiled. And what do I mean by m bar? M bar is the mod 4 reduction of m. Okay, so in particular, what I mean is m bar is between like 0 and 3. Okay. Does that sort of clarify what's happening? So, right?
Yeah, or actually, I think we can do it without taking away columns. You can just say that 2 appears when the column number is modulo 1 or 2 uh, is is congruent to 1 or 2 modulo 4, and the rows that are and the same thing for the row number.
Uh,
And we can count these and find out that they are more than 1/4 of the area.
okay, so you're talking about counting twos and you're saying, um, okay,
It's either 1, 2, or 2, 1, modulo 4. Row and uh, row and column.
hmm, okay, okay, so, okay, I just wanted to write it this way just because I think sort of, at least for me, it's clear this way that like, okay, all that matters is the value of m modulo 4, right? Because we said, okay, yeah, like, okay, let me sort of say, um, sorry, I've sort of lost my train of thought. Um, but okay, if we're interested in checking, right, if the colors are equally distributed, we can do that check just by considering m and n modulo 4. Okay, and then it becomes very simple. You can just like okay, if m and n are both even, then okay, if there's a 2 by 2, it doesn't work anymore, right? So okay,
Yeah, I think the easiest way to do this is to just take the chunks from the right and the bottom, and then we know that we are left with 1, 2, 2, 3.
yeah. I also think it's the easiest way. You can just remove some chunks that are all have, equal distribution of the 4 colors, and you're left with a 2 by 2, and it doesn't work. Okay. I hope um, of course, all these other ways, they're good, and they're probably roughly equivalent, but okay. Um, okay. Um, are there any questions? I know I didn't actually write the proof, but maybe I don't want to do that because I don't want to I'll probably, get lost trying to write it formally. So I'll leave it as an exercise or something. Um, but yeah, are there any questions or comments?
No, I think we can make writing the proof much easier if we just leave the 4 squares on the up left.
Um, yeah.
Since we started, yeah.
Yeah. Okay, so how about this? I'll leave the proof as an exercise. So, okay, for homework, you can actually write this problem however you want. You can use this method or a different method. And okay, I think it's a good problem. This is a good problem to write up because it's there's a lot of technical details that you can lose points on in the IMO. So, okay, if you want, you can write this for homework. I think it's a good exercise. We already know how to solve it, but it's a good exercise to write formally. But okay, let's just look. To summarize, what was the idea? We did this coloring and we said, okay, if you can tile it, then every color shows up the same number of times. And that can only happen if m or n is divisible by 4. Okay, so yeah, so this is good. The key was to find this coloring where every tile is equally covering. Okay. Um, okay, so let's now go let's go. Oh, by the way, no. So Kareem, I think I now understand what your other solution was. So maybe I'll just point it out because I think it's good. So tell me if this is what you had in mind. So I think so. The coloring that another one you can do is you can do a two coloring. How does it work? It works like this. Um, so it's like okay, it's like 1 1 1 1 2 2 2 2 1 1. Is it like this?
Yes, it's the same thing, but it makes it easier to
Uh,
count.
I agree. Now I understand. So you're right. So and so it has the same property. Every tile is equally covering. It's two of one color to the other color. And you're right. So now this should be easier to think about. So I will
How
okay.
will we do this?
So like
The
so
tiling was an odd number.
sorry, the
What
tile.
if we had like it's tiled by 1 times 5?
Well,
How
and
would we do it?
so we can assume we're in the situation where both m and n are even but not divisible by 4. Because by area, we know the total area has to be divisible by 4. Do you see?
Yeah, I'm saying what if like the tiles, not the board, the tiles were like
Ah.
1 by 5.
Okay, so we will get there, right? So we'll go there in a moment. But so in this case, I want to point out that since 4 is some small number, we have this nice argument like this, and I think this one is actually cleaner because it's easier to count. So I won't go through it, but I'll point out that this coloring is I think it's a easier coloring to use.
Doesn't this also work for checkboard coloring?
Uh, if you do checkerboard, um, it's true that every tile has equal red and blue, but the problem now is I can take like 2 by 2 and 2 by 2 has equal red and blue. But
Okay.
this coloring 2 by 2 won't. Do you see?
I see. Yeah, yeah.
So this is a very clever coloring. It's very okay. So okay, we have 30 minutes left. I wanted to talk about two things. So I wanted to talk about so the two topics I wanted to talk about still are sort of fancier colorings. But we will come to that later. I want to talk about the generalization of this problem when you have instead of 1 by 4, you have 1 by k. So it's what you were asking. Adham, that's what you're asking, right? About like 1 by 5 or 1 by 7 or something.
No, I'm saying in the case of using two colors, it wouldn't work for an odd number of time.
Yeah,
Like
yeah.
this would work for 1 by 6, or it wouldn't work for a 1 by k.
So you're saying this method here will work if I have 1 by k, for example, right? This is your
Yeah, supposedly yes.
yeah, so let's actually just sort of do that. Let's go and I want to say more about that. So this is problem no, I skipped now. I want to go to problem 9. Okay, so this is problem 9. Um yeah, so for which m by n can you tile by a 1 by k? Okay. Um okay, so I skipped some problems, but we'll go back to those. I want to do this now because it's kind of what we're already talking about. Yeah, so okay, so of course the area should be divisible by k, but if we want to continue by analogy to the previous thing, our conjecture, let's not call it a claim because we don't know, let's call it a conjecture. Yeah, so what's the conjecture? Which m and n will work?
If M1 is divisible by k.
Yeah, right. So yeah, it can be tiled if and only if m or n, okay, if and only if k divides m or k divides n, right? Which is not at all clear from area, unless k is prime, but that's kind of not interesting. Okay, so right, so Adham, the coloring you proposed, we can actually do it again, right? We can say, okay, let's take this, take our board and can go like this. So we do 1, 2, 2, 3, 3, 4, and okay, so somehow we have to say, okay, we go all the way up to k, so we maybe do k, 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 and then we do k, and then we do 1. We do, okay. I'm not doing a good job of explaining, but do you guys understand the coloring that's proposed here? It's like you go 1 through k, and then you repeat. Does it make sense, the coloring here?
Yeah.
Okay, so I want to, so, okay, why did I call this section coloring beyond colors? There's an easy way to say what this coloring is. Can you think? Like, okay, if I have like, okay, let's say I number the positions 1 through, which is m, 1 through n, and then 1 through m, right? So if I have the position I comma j, what color do I put in I comma j?
We put j minus I mod n.
Is it j minus I? Yeah, it should be something like j. So what is this? If I do j minus I think if I do j minus I, it will be the
No,
diagonal
it's not.
will go this way, right? Which is okay, but
Oh, no, it's not. No, sorry.
I mean, it's basically j minus. I mean, j minus I would do with the diagonals would be this way. It's j plus I is what it is, right? Or I plus j, right? It's okay, basically the same thing. So this gets colored with I plus j mod n. Okay, maybe is that right? Okay, that means we start with 2 or something. Okay, that's fine.
-1.
Yeah, minus 1. Okay, so it's not okay, it's not that big of a deal, but okay, whatever. Like I plus j minus 1, it's the same thing. It's just relabeling the colors. But okay, so the point is we're not really coloring with colors, we're coloring with things that have more structure. We're coloring with like residue classes, like okay. Like classes mod n. Okay. So now what's the idea? Every tile of size k is going to cover one of each residue class, right? It's going to cover one of each residue class. Oh, not mod n, sorry, mod k. Did we I wrote mod n, but it's mod k. Okay. And the point is each tile is now going to cover each residue class exactly once. Does it make sense what I'm saying?
Yeah.
So
Yes, and the residue class will be complete. So it will contain all numbers from 1 to k.
yes, it'll continue all numbers from 1 to k. And in fact, each number will occur. So that's for each tile. And it means in the whole thing, each residue class has to show up an equal number of times. Okay, so it has to sort of be evenly colored. Yeah, if it's tileable. So we have this question of when is it true that if I label or if I color the board with classes like residue classes like this, when is it true that each residue class shows up an equal number of times? And okay, we should try to show that it's true if this condition is satisfied. Okay, and you can use a similar argument where you cut off like okay, you cut off blocks of size k and then you reduce to the case where m or n is less than k. Right? So you can do that. Does it make sense what I'm suggesting? It's the same argument as before. You can sort of like cut off blocks of if I have some 1 by k, I can cut it out. But okay, so does it make sense that should be able to work that out? but
Yes,
I'm
we will have at the end a board of N prime and N by N prime, where N prime and N prime are between 0 and k minus 1. And we prove that for all M prime and N prime less than or between 0 and k minus 1, we can't tile it by 1 by k tiles, and we are done.
great, excellent. So we reduce by these cutting off these boards, we reduce the case where M prime and N prime are between 0 and k minus 1. And that case is great because you can't even fit, unless one of M prime and N prime is 0, you can't even fit a single tile. Right? Does it make sense?
Yes.
Okay. Good. So that's one solution. I want to give a slightly different, really the same, but slightly different solution, which avoids this whole reduction argument where you don't have to think about cutting off these blocks of size k. I don't know if it's easier, but I think it's nice, and it sort of illustrates a point I'm trying to make, which is sometimes you don't color with colors, you color with something more. So let's discuss what is the thing I'm doing. So okay, so I want to use like this. So our coloring before, it was something like, you color with residue classes. Okay, it's a very nice coloring. But what I'm going to do now is something that's a very, very clever trick. So I'm going to color with, I'm going to say, let omega be a primitive nth root of unity. Okay? So, yeah, so what's the idea here? So what is a primitive nth root of unity? I mean, omega to the n equals 1, and omega to the k does not equal 1 for k between 0 and n. Are you guys familiar with this, what this means?
Yeah.
Okay. Yeah, so
Can't you also tile by roots of unity as well?
that's what we're about to do. So, but okay, I want to make sure what we know what roots of unity are. So, is this a notion you guys are familiar with? These nth roots of unity. So,
Actually, I'm not familiar with it.
okay, so it's it's Karam, do you know this thing when we multiply complex numbers? So this is the complex plane, this is the real axis and the imaginary axis. If when I multiply two complex numbers, the magnitudes multiply and the arguments add. Do you know this this fact, or do you know this idea?
Could you go over it again?
Yeah, so okay, so maybe okay, I won't say too much because I think maybe this is something we'll have a class on complex numbers at some point, but okay, what is the idea? That if I have two complex numbers, so there's something called the magnitude. That's okay, so if I like 3 plus 4i, what is the magnitude? It's the square root of 3 squared plus 4 squared. It's the length. I can write it. The length from the distance from 0. Okay, that's the length. And what is the argument? It's like the angle to the real axis. Okay, so it's this angle here. So when I multiply two complex numbers, their magnitudes will multiply and their arguments, I'll write it like this, will add. Okay. So does at least the statement make sense, Karam?
I see why their magnitudes are multiplied, but why their angles are added.
Okay, so this I will suggest I'll give you some reading. Okay, I don't think we can. This is not something easy to cover in class. Okay, but yeah, so I suggest we do some reading. Okay, But the result that is very nice that follows from this is okay, what does it mean? It means that if I have a number z, so that z to the n equals 1, this is the nth root of 1, it means that the argument of z, so where is 1? 1 is here. It has magnitude 1 and argument is 0. Means the magnitude of z is 1, and the argument of z will be a multiple of 2 pi over n.
2 pi k over n.
Yeah, 2 pi k over n, that's right. Because I need n times the argument to be 0. Does this make sense, Karam? If I assume the other thing?
Yeah. Because we want the angle to return to the x-axis,
That's right. We
but
want if I do n times the angle, right? When I take to the nth power, I'm adding the angle n times. I want it to return to 0 after n times. So the angle should be 2 pi over n times the integer. So it means that the solutions, they are in a uniform circle around of radius 1 and space n of them spaced equally. Okay. So if we just pick the first one, okay, this is a primitive root of unity. Okay. So it has length 1 and angle 2 pi over n. That's what I want to pick omega. Okay. Okay. So Karam, does it make sense what this number omega is?
Omega must be like all omegas must be in some circle, and these points like bisect the 2 pi or something like this.
Yeah. So okay, I didn't quite. How about this? Okay, so Karam, I will send you a reading on roots of unity. Okay, so but for now we'll just okay. I think this is maybe the most explanation I can give. Okay, so that's what I mean by root of unity. It's omega. It has length 1 and angle 2 pi over n. So why did I want this number? I wanted this number because I want to now label this grid. I want to label this m by n grid not by residue classes. I want to label it like this. I want to put I want to put omega here, then omega squared, omega squared, omega cubed, omega cubed, omega cubed, omega 4, and so on. Okay. And of course, okay, when we get to omega to the n, it's the same as 1. It's just omega to the 0, right? So it's like the same thing as the coloring by residue classes, but we think of them as complex numbers rather than residue classes. Does it make sense what this coloring is?
Yes, it's like the first one.
Yeah, it's very similar, but instead of being a residue, it's okay, it's like it's just maybe
And we can
yes.
and we can't have w to the I equal to w to the j for I and j less than n, and I does not equal j, because that implies that we have a number less than n such that w to that number is 1.
Exactly, you're exactly right. So they repeat only every n. Okay. Exactly. Also, I realized I want to actually, okay, doesn't matter that much, but I want to actually change the indexing so it starts at w to the 0. It's not super important, but I think it will be
But
better.
I think it's similar to the exponent modulo n.
Yes, it is, yes. So it is the exponent. Yes. So I will do it like this. So the first one will be w to the 0. Okay. Now, what is the point of doing it like this?
Yeah, because the sum
Exactly
of
right.
the roots of unity is equal to 0.
Exactly right. So now if I take a tile of size, did I say nth root of unity? I meant kth root of unity, right? Okay, so sorry for the confusion. I hope that you guys can forgive me, I meant kth root of unity, right? Because so you have a kth root of unity. Okay. So now what is the point? The point is any tile now. If I take any tile, okay, it covers each root of unity exactly once. But the point is that if I add the roots of unity, I get 0. So if I take w to the 0 plus w to the omega to the 0 plus omega to the 1 plus all the way to omega to the k minus 1, this sum is 0. Okay, so this is there are many ways to prove it. The simplest one is just, okay, I use geometric series formula. It's like this, and this is just 0. Okay, so the sum of any tile is 0. Does it make sense?
Yes.
Okay, so what does it mean if you can tile the board? It means that the sum of the whole board has to be 0. But what is the sum of the board? Can anyone tell me?
It shouldn't really be 0.
Well, so okay, if it's tileable, it should be 0. But my question is, can you express the sum of the can you express the whole sum of the board in a very nice way?
Maybe summing in the sum of each column or each row.
Okay, so each column is like, okay, so let's do it. So I need more space, right? So okay, let's create another page. Okay. Yeah, so let's remind ourselves. It's something like, okay, we have 1 omega 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 square omega square omega cube like this. Okay, and so what is it? There's m of them here and there's n of them here. So if I do the first column is going to be 1 plus omega square all the way to omega to the m minus 1. M minus 1, yes. Okay. And then second column is going to be, okay, it's going to be omega plus omega square plus all the way to omega to the m. But really, this is omega times the first column. Do you guys see it?
Yeah.
Okay. Do you guys now see the whole sum, what it's going to be? Like, what is the third column? Third column will be omega squared times the first column. Do you see it?
Yeah.
Uh,
And so the
it,
sum of the first column is 0.
Well, we
Or
don't
if
know.
if it's k divides m, no?
If k divides m, the first one is 0, but we're trying to now think under what condition will the whole sum be 0?
Either when n divides k is equal to 0, because then we can take the common factor, which is the sum of the first row, and you multiply it by the sum of the w omega times omega plus omega to the power of 1 plus omega to the power of 2. So you only get that it's 0 if n also divides k.
Okay, yeah, so let me maybe we need to try. What is the total sum? The total sum is going to be, it's going to be one,
It will be the first row times first column.
exactly right. It'll be, so each column will contribute this times a factor, and the factors are like this, right? It'll be exactly like this. Do you guys see? It's the sum for the row and the sum for the column. That's the total sum, which means it'll be 0 if and only if one of the factors is 0. And now
Yeah.
okay, it's very nice. Like each factor is 0 if and only if like the exponent is divisible by k. Right? You see, so this is some of the very nice fact that like you can factor the total sum. So it's going to be 0 if and only if either the row or the column is 0. So it tells you either m or n is divisible by k. Is it does it make sense? Are there any? What is it? Is it clear what the explanation is?
Yeah, it's clear.
Okay, so there's some kind of magic happening here where like I don't know, like this the fact that you can write the sum and add factors is and it's okay. I don't know. At least when I saw this solution, I was like, okay. Um, okay, so I had wanted to do some more problems, but I don't know, I'm kind of tired and also okay, so maybe I'll ask you guys. So I had wanted to do okay, there's problem 7 and there's problem 8. Do you guys want to continue with the lecture today, or do you want to, I know, what do you guys want to do?
It's okay. It's just whatever you want.
Okay, I see.
It's fine if we end. It's fine if you continue to.
Okay, I see.
I kind of have to go, so I wouldn't be able, but I would watch the recording.
Okay. Okay, so the thing is I also want to give you guys time to think about this. Um
Oh, it's okay. We can end if you want.
yeah, I think because I want you guys, let's do it this way. Uh okay, let's do problem 7. I think problem 7 is a good problem because it illustrates something I wanted to talk about. So we'll do one of them and yeah. We'll do one and the other one can be homework. So we'll just go over time because okay, we'll do problem 7 and I want to give you guys some time to think about problem 7 first. So
Bendik,
yes.
is it okay if I leave now?
Yeah,
Because
that's
I
okay.
have
That's
to go,
okay.
but I will watch the recording.
Yeah, that's okay. That's
Oh,
okay.
thank you.
Um yeah, so let me define what is a closed night's tour. So what I just mean is okay, I just mean like the night starts somewhere and then it visits every single square and it comes back. Every single square exactly once, and it comes back to the starting point. That's just closed just means it comes back to the starting point. So is it clear what the
Yep.
meaning of this is? Yeah.
Yeah.
Yeah. So I'm asking on a 4 by N board, um, is there a closed night's tour? Okay. Yeah, so maybe think for some time, try some small cases. Oh, and sorry, the problem is phrased a little bit different. It's a little bit strange. Like for which n is what I mean. For which n is there? You guys understand, right? Okay. So yeah, let's take some time to think.
You have to get back to the beginning, the point where you began. Okay.
Yes, so yeah, the closed part means you have to go back to the starting square. Okay, do you guys want more time to think, or should we discuss?
A bit more time.
Okay. Okay, shall we discuss now?
Yeah.
Okay, yeah.
Okay, so I hope you guys are able to think about some small cases and So okay, let's first talk about the checkerboard coloring, right? So it's not enough to solve the problem, but okay, why is the checkerboard coloring useful here? Because when a knight is walking, it's alternating colors. Okay. So okay, I mean it's not useful because okay, it tells us, since it's alternating colors and it comes back to where it started, there's an even number of steps, but okay, 4 by n is always even. Okay, so if it was like 3 by 5 or something, checkerboard will tell us it's not possible, but okay, in this case, checkerboard is not enough, right? But it's important because you have this thing where it alternates colors. But there's also another way in which you have alternating in this problem, right? So yeah, so what do I mean? So I drew some pictures, but okay, let me just make another one. So yeah, so if I have like this 4 by n, right? So I have 4 here and n here. One thing the knight is gonna do is it goes from, okay, there's like these 4, you can think of them as like there's there's 2 outer layers and then there's an inner layer. Yeah. And the knight, it always switches between outer and inner. Does it make sense? So like if it's here, it has to go here. So it's like oh no, sorry. That's not quite true. That's not what I meant. That's not true actually. Does not do this. Okay. Yeah, because you can go from here to here, right? So it's not true actually. Yeah, the knight is not actually switching between outer and inner. Okay, that's not true. Yeah, so that's not quite true, but what do I want to do? I want to, okay, maybe that's not true, but I still want to say this. I want to do a coloring where I like, okay, where I like, so what I said is not quite true, but I want to take this coloring where I have like the outer and the inner, and I want to overlay it with the checkerboard coloring. Okay, so I want to combine this plus checkerboard. Okay. So you can think of it, it's like I'm making the checkerboard coloring stronger or something. So what is the result of that? So the result, yeah, so how do I draw this? Let's do like this, 0, 1, okay, like this. I know, I'll use these letters. I don't know if it's the best letter to use, but okay. And then what? So then these layers get labeled like this. 1A, A1, so on. And then what? So then here they will be labeled like this. Do you guys understand what I did here? I combined two colorings. Okay, so one is the coloring where I have inner and outer, other one is checkerboard, and the result is this. Does it make sense?
I think so.
Yes.
Okay, so yeah, so make sure like, you know, okay, I don't know if I did it in the best way. Maybe we can use highlighter to make it clearer, right? So it's highlighter, that's highlighter, right? So yeah, like this. So that's the checkerboard. Okay, and then it became what? So it became that if you're so one of the checkerboard, let's say black, became 1 and B. B is outer, 1 is inner. Then the other checkerboard, white, it became 0 and A. 0 is outer, A is inner. Does it make sense?
It does.
Okay, so what was the point of all of this? The point was now, well, look at, let's look at, for example,
Yeah, we can just go through all zeros at once and then switch to A's and B's.
yeah. So I mean, what's the problem? The problem is like look at 0, right? If you want to get to 0, I should use this. If you want to get to 0, the only way is to go through 1, right? Like 0 is like a knight to get to 0 has to come from 1 and exit through 1. Okay? But now you see the problem, right? Like if to get to 0 you have to come from 1 and exit from 1, there has to be more ones than zeros. But that's just not true. There's equal number of every color. Do you see? Like if I write down what the sequence is, right? Like, okay, it's gonna be like 1 0 1 0 1 0, some amount of these, and it has to end in 1 because I can't exit from 0. I can only exit from 1. So I have some block like this, and I have some block that's like A, B, but you know, it like what happens? Like from 1, okay, like I can't go to B, I have to go to A. So it goes like A, B, and it ends in A. So like you see, if I do this, there's gonna be more A's than B's and more ones than zeros. Do you see?
Yeah.
And so that's just a contradiction because like I need to cover every square equal number of times. Does the
Yeah, it makes sense.
guys, is it okay? Abdullah and Karam.
Yes, it does make sense.
Yeah, I mean once you do this coloring and somehow it's kind of miraculous.
But
Mhm.
how can I think of this idea? It's hard to think of it.
Yeah, so that's a good question, right? So how do you come up with
What's the motivation?
yeah, how do you think of this color? That's a good one. Um so to be honest, I came up with it using the wrong idea. I thought you have to alternate between inner and outer, but that's actually false. Um so now I don't know how to come up with this idea. So let's see. So somehow, okay, what is this coloring? First of all, it's not a coloring, it's actually two colorings combined. Okay. And so yeah, so somehow you have to consider the idea of thinking about the inner layer and the outer layer. How do you think of that? I'm not, honestly, I don't know. I mean, the idea is, okay, if I'm at an outer layer, the previous and the next step both had to be from the inner layer. That's sort of the how you have to think about it. Like if I'm in row one, right, this is row one. Where did I go? Where's my pen? Yeah, so if I'm in row one, I had to come from row three. Okay, and if I'm in row four, I had to come from row two. Um, I don't know. I don't know if it's sufficient motivation, but okay. It's a very clever idea, but that's sort of maybe how you think of it, right? You want to combine checkerboard with thinking about the layers. Okay. Um, okay, yeah, so any comments or any questions?
What would we study after combinatorics?
Okay, good. So, well, before we do that, let me just make some comment. I I wanted to discuss this problem, but that will probably take us to 7:30. I don't know if we have time for that. So, yeah, so this problem will be homework. Let's say this. There's a lot of homework problems. Some of them are harder than others. If you get stuck, please message me. I'll give hints. Like a lot of the problems, I can even after you know the coloring, it's still not easy. So, like if you want some kind of hint, please ask me questions. Yeah, okay. And so the homework problems, okay, there's some, I just found on the internet, but most of them will come from this note by Yufei Zhao. This is talking about problem 16, and he has a bunch of problems. So, okay. But also, the other ones are also good. You can take a look. So this is problem 14, which is a generalization of this m by n and 1 by k. Okay. Yeah, so there's a lot of problems here. Okay, and then what are we doing next? So we can do one more combinatorics. I think let's see, we've done counting in two ways. We've done coloring and tiling. So, okay, I know over the summer we already did invariance and monovariance. So I don't think, yeah, maybe we don't do it again. Do you guys want to do more combinatorics or do you want to switch topics? That's what I'm asking. Oh, also let me stop recording. This is not important anymore.